the work I'll be presenting today is joint work with Samuel Christie and Muninder Singh, who are at North Carolina State University in the States, and I myself am an academic at Lancaster University. So our program of research is to think about abstractions that enable building loosely coupled, asynchronous systems. How do we build such decentralized systems that are loosely coupled, asynchronous, and that capture the autonomy of the components? So interaction-oriented programming is all about that, and I'll give you a flavor of its capabilities in this talk. Okay. So the talk is in three parts. I'll go over the context and philosophy. What is sort of the driving philosophy behind our work? What is the wrong stuff that people do today? And what is the right stuff? The right stuff obviously contains elements of our approach. Okay, so this is the structure of the talk. Okay, so the way we think about systems, my group thinks about systems. We think of systems as being socio-technical in the sense that they have autonomous principles who are interacting with each other to exchange some services or goods, whatever it might be. So, for example, it could be a system for e-business where you have buyers, sellers, shippers, payment agencies interacting with each other to achieve some purpose. It could be in health, for example, when you order a test from a laboratory. It's the GP who does, the doctor who does it. You have to give a sample to the laboratory, you get results back. So there are many autonomous parties involved in these interactions. In finance, the same way, if you're doing a trade for any financial instrument, many parties are involved, not just the financial institutions, but settlement agencies behind the scenes. Many kinds of autonomous principles are involved. So these are all socio-technical systems because there are social autonomous principles involved. And they're conceptually decentralized. They're decentralized because each principle is a locus of decision making. It has its own internal reasoning, its business policies, and it interacts at arm's length with other principles via messaging, by sending messages back and forth. Okay, so they're conceptually decentralized. Now the challenge for software is how do you realize a socio-technical system in a manner that reflects this conceptual decentralization and that results in a loosely coupled system that lets the principles interact with maximal flexibility. That's the key thing, maximal flexibility. Because if autonomy is not flexibility, what is it? Right? It's nothing. So multi-agent systems is a field in computer science that has been dealing with such settings, approaches for such settings. And there the idea is that each principle deploys an agent. An agent is a piece of software. Nothing very fancy about it. They don't have to be the AI agents of today. They could just be old-fashioned Python agents, running some business logic coded by the developer. So the point is that each agent represents the principle and interacts on that principle's behalf with the agents of the other principles. Okay? So now you get a decentralized system. You have these 4 agents, each representing a principle, and they're interacting by sending and receiving messages. Now, the agents are heterogeneous in construction, meaning that each principle could deploy its own technology stack in creating the agents. They reflect the autonomy of the principles because they encode the decision-making of the principles. So, for example, at what price does a seller want to offer some goods? That's the seller's internal reasoning. It's not part of the public interactions. And they interact based on agreements and asynchronous protocols. So agreements are just what they are in real life, right? In any business engagement, you have contracts that define what the parties are supposed to do. So that's all that is. So interact based on agreements and protocols. The protocols define the operational constraints on messaging. Okay, and these protocols have to be asynchronous because synchrony in general is bad. You want to minimize synchrony. So what is interaction-oriented programming? It's a method to model a system as a multi-agent system in terms of the interactions between the entities in the system. So first, before you build a system, model the interactions between the entities in the system. Then we can compose and verify those models. So before you actually even implement any agents in code, you compose and verify the system model. So we have formal languages in which you can do that. And then once you have the formal model, anybody who wants to play a role in the system can implement their own agent accordingly based on the model, separately from the implementations of the other agents. So you have independent agents implemented. Our driving aim is we want high-level abstractions that reflect stakeholder intuitions, that capture the intuitions that the entities engaged in the interaction have about their setting. So we want high-level abstractions. And we also want abstractions that let programmers focus on the business logic. So that makes their task very easy. So now let's look at some of the wrong stuff. So we want to model a system as a decentralized system. We want to do that because there are autonomous parties involved in the system. So it is conceptually decentralized. But what do we do today? Well, we build a centralized service. And the centralized service mediates all the interactions between the users as principals as users. So that's not great. Now we don't have a decentralized system. We have one piece of software, and it's a client-server setting. Microservices aspire to decentralization, but so you could take up a service and then you could divide it up into microservices, which could be developed independently. That's all good. But they are hobbled by things like orchestration, that you orchestrate the microservices, which is a centralized paradigm, or RPC, that you just do request response. Or I've seen examples in microservices frameworks where the microservices actually use a shared database for communication. That's not great. If you want to be decentralized, you cannot have a shared database. Or they just resort to using PubSub as a low-level communication service. So there is no discipline in how the microservices are programmed, but they use PubSub. It gives them asynchrony, but it doesn't help actually program the microservices themselves. So here's an interaction protocol from HL7, which is health level 7. So they create standards for messaging between healthcare entities. And they specify the messages, their schemas in gory detail. And that's all fine because it's a complex setting. But then when they have to specify the interaction protocol, so this is a laboratory where you use a laboratory for testing a specimen from a patient. And this is how they draw the protocol as a workflow. And there are so many entities involved. Now, this is quite complex. It is very rigid because all the activities are ordered highly sequentially. And it is complex, so complex that when programmers actually implement this workflow in code, they end up creating something different. There is no way to go from this model to actual running code systematically. So what we need is a programming model that can take a model of a protocol and based on that, let you create the endpoints that you want to create. So far, so good? Or we have, think about the current distributed systems paradigm. It's solipsistic. They are focused on providing message ordering guarantees and reliability guarantees. So this is a typical stack you'll see underneath any application. So you might have the internet, of course, provides the basic communication services. Then on top of that, people assume TCP. The whole web runs on TCP, right? It assumes, HTTP assumes TCP. So you have TCP. Then if you're building an enterprise application, you might have message queues or something like that provide ordering. So TCP and message queues both provide ordering guarantees, right? Between any two endpoints, they'll deliver messages in FIFO order, first in, first out order. And they'll also provide reliability. They'll make sure that your messages get across to the other side. So we don't today model the application, but the application relies on complex middleware to get the job done. This, of course, violates the end-to-end principle, which says, communication services must be simple and any coordination must really be left to the application level because the application knows best. But today we don't model the application. Instead, we sort of rely on complex middleware. So think about, so here's a couple of points to ponder. Think about message ordering in communication services. My claim is message ordering, like for example, the thing that TCP or message queues provide, the FIFO ordering, and even more complex ordering like cause of delivery and so on, they are unnecessary. You don't need that. And here's an example. A patient can send a complaint to a physician. So this is a protocol, in an informal notation. A patient can send a complaint to a physician. The physician can then send a prescription to the pharmacy, and the pharmacy can send a fulfilled message to the patient. Now think about this. Must the pharmacy receive prescriptions in the order sent by the physician? It's a question for you to answer. I see a no over there, and that is because they are independent, right? Any two prescriptions are independent, so the pharmacy can handle them in any order, right? So why do we need ordering in the communication service? We don't. What about the second one? If a physician sends prescription followed by its cancellation, so the physician sends a prescription off, then realizes she has made a mistake, and then she sends a cancellation to the pharmacy. Must the pharmacy receive them in the same order? I see a no. Any yeses?
If the cancellation has a reference to the following,
Great.
then it's fine.
Right.
If not, then it's
okay. So I got some great answers. I wasn't expecting that, but that's great. That's great. So I've also heard answers where, and people do this a lot. So they'll say that the prescription must be received first, because if you receive the cancel first, you don't know what it's about. But like the answer just I heard, the cancellation will have a reference to the prescription. So when you get the cancellation before the prescription, you know that you've received, there's a prescription in the air, because a cancellation could not have been sent without the prescription being sent. So there is a causal dependency there. You can't send a cancellation without the prescription. But the pharmacy can receive them in any order, because if it receives the cancellation first, there will be a reference to the prescription. So the meaning of the cancel is meaningless unless it has a reference to the prescription. And therefore, the pharmacy can handle them in any order. If it receives the prescription later, if it ever receives it, the pharmacy can just say, well, I've already seen the cancellation before, so no need to do anything here. Right? So now think about it. Independent messages don't have to be received in the same order. And when a message depends on another, still they don't have to be received in the same order. So which two messages ever have to be received in the order that they were sent? Think about it, and we can discuss it later, okay? My claim is no two messages have to be ever received in the order that they were sent. And this is just FIFO, but people have invented all kinds of complex ordering guarantees, including total order and so on. We don't need any of that. We don't need any ordering whatsoever. Now think about reliability, right? So our communication services like TCP, message queues, they also provide reliability guarantees, meaning that if you send a message, they'll guarantee it gets across. Now consider the same scenario where they're communicating through reliable communication service, right? So messages do get across. However, the patient times out waiting for fulfilled from pharmacy. So a failure happens in the patient's code. It times out. Why does that happen, you think? Communication is reliable, messages are getting across, but the patient still times out. Well, because as often happens in my case, maybe the physician is sitting on the complaint. For whatever reason, they may be too busy, or they may not be available for some reason, or the physician may have sent a prescription, but the pharmacy may not have acted upon it, right? So even though you have reliable communication service, failures still happen. Then what do? Well, I call up my GP practice and I ask them, well, what happened to my complaint? So you are doing fault tolerance at the application level, isn't it? And there is no avoiding building such kind of fault tolerance when even in software systems, you have to apply the same logic. But once you start doing fault tolerance at the application level, you don't need the low-level reliability guarantees. Because you're doing it at the application level, you're doing descending messages or forwarding messages when you want. So why do you need reliability from underlying infrastructure? You don't need it, right? So now we've gotten rid of so much complexity from the stack. We don't need ordering, we don't need reliability. Think about this example. So here, there are three parties, the buyer, seller, and bank. And now this figure on the left shows the protocol between them, okay? So this is a UML interaction diagram, and people in academia and industry often use these diagrams to depict protocols. You could use state machines, they'd be just the same, analogous. So the seller sends an offer to the buyer sends an accept to the seller, saying, I accept your offer. Buyer then sends an instruction to the bank to make the payment, upon which the bank does a transfer, right? So this is the protocol. And we want to design endpoints for buyer, seller, and bank based on this protocol. So far, so good. Now, what could happen in practice is the accept could arrive after the transfer, right? Just because of asynchronous, just because of delays in the network. So you imagine that the execution would go like this, but because of asynchrony in the network, so delays in the network, you get the enactment depicted in figure B. That means the protocol is violated. So now you have two choices. You have to say either this is a bad protocol and reject it, or you try to make it work by saying that, well, the seller is not going to listen to the channel from the buyer till it gets the transfer and till it gets the, not listen to the channel from the bank till it gets the accept from the buyer. So you're doing reordering inside the agent, right? But in real life, but we don't want to do this kind of reordering, right? Because you cannot say, I don't want to receive messages from you now. I want messages from this party now. You can't do that. You receive what you get and make it part of your state. You can act upon it when you want to, but you can never choose when you receive something. Okay, that's the basic principle of asynchrony. You never get to choose when you receive something. And in real life, actually, it's perfectly reasonable for the seller to, when it receives a transfer, even if it has not received an accept, it could say, well, I got the payment. I could just go ahead and do the shipment, even if I have not seen the accept. Right? So in real life, interactions are much more flexible. But when we sort of conceptualize them like this in terms of UML interaction diagrams or state machines, we draw them very inflexibly and they cannot be enacted properly in decentralized settings. So my claim is this, that today we are living in a geocentric world when it comes to modeling and implementing interactions. The conventional wisdom in particular is outdated. Programmers implement interactions today in low-level code, saying send, receive, channels, all this kind of stuff, with no actually model of the interaction. You want to model stuff so that then you can use the model to build stuff. They have a synchronous mindset which favors message ordering over meaning. Instead of figuring out what is the meaning of the message, like we discussed in the cancellation example, that is an element of meaning, that the cancel is meaningless without a reference to the prescription. Instead of modeling stuff properly, we favor message ordering. Let's just receive messages in the order sent. So we have the synchronous mindset, so we got to get rid of it. We rely on needlessly complex communication services, and we cannot model flexible interactions. Without flexibility, again, autonomy is meaningless, right? So what is the right stuff? The right stuff we've been working on for a while, and one of the elements of the right stuff is this language called BSPL, the blindingly simple protocol language, in which you can specify interactions very flexibly, in which there is no ordering on messages in the sense that no two messages have to be received in any order relative to one another. And this is, so I want to, in the next few slides, I want to give you a flavor of what this protocol language looks like and how easy it is to formally specify a very flexible protocol that can be enacted in a decentralized setting. Okay, so in this language, the protocol specifies the computation of a decentralized information object. So this object is not materialized in any central location. It's distributed across the agents. And the computation happens via communications, via messages. The messages convey knowledge and meaning via parameters. So messages have a schema, right? They'll have some parameters. Like, for example, offer will have the parameters ID, item, and price. That conveys the meaning of the offer, that it's this item for this price. The key parameters identify enactments. So, for example, offer has ID is key, so it identifies the business enactments, could be used for correlation and so on. And the causality adornments determine when an agent may send the message in an enactment. So out means the parameter's value or binding may be generated if not known. In means the parameter binding must be known from prior interactions. So out means you don't know the value, but you can generate a value. In means you know the value from prior interactions. And there is a third nil, which I'll not discuss because I'm not using it in the example. So for example, in offer, all the three parameters, ID, item, and price, are all out. So that means the seller can send the buyer an offer at any moment by generating values for them. Okay? So now you want to specify this e-business protocol flexibly, right? So I showed you the e-business protocol over here, and this was not good. It was inflexible. It doesn't support asynchrony. It's bad. So now you want to do it flexibly. So what do we do first? You focus on the meaning of the messages. Okay? So the meaning is just, what are the parameters that make a message meaningful? Every message has to be self-contained in terms of meaning, right? Just like REST, things have to be self-contained. So here's the e-business protocol. It has roles buyer, seller, and bank. It is computing tuples of this kind, ID, item, price, payment, and status. So this is what the protocol is computing via these messages. And here I've given just the meanings. I've left out the adornments, and we'll fill in the adornments in a minute. But the meanings, so offer says, it has parameters ID, item, and price. Accept is, I accept this item for this price, and this is the reasoning for my decision or something. Instruct is from the buyer to the bank, that make a payment corresponding to this price, and here's the details. So, you're capturing only the message schemas, right? There's nothing else to it, just the message schemas. Now, once you have the message schemas, you can start addressing a coordination requirement. So if you say offer is the first message in the enactment, you make all its parameters out, because it can start a new enactment. So all its parameters out. Accept can happen anytime after offer. Not right after offer. It can happen right after offer, but it can happen anytime after offer. So what does it mean? So we make ID, item, and price all in. That means it must know them from a prior communication. And when the buyer receives the offer, it will know the values for ID, item, and price in that enactment. And at that point, or any point after that, the buyer can send an accept. And it can generate a decision, because, that's what it does in the accept. Instruct can happen anytime after offer, and transfer after instruct. So in instruct, we make ID and price in and out the details. So that means it can happen only after offer, because offer is generating them. And likewise, you want to make transfer dependent upon instruct. We don't want the bank to do a transfer unless it has seen an instruct. So instruct generates details. It also details, but we make it in transfer. So that means without seeing the instruct, the bank will be unable to do the transfer. So what are we doing? We are specifying information causality between the messages, information dependencies between the messages. We are specifying what does an agent need to know from prior communications to be able to send a message. Okay? And that's a very powerful notion, the notion of information dependencies. And the last requirement is shipment after offer. Okay, so that means whatever's out in offer, wherever they appear, we can make them in shipment. So ID, item, and price are in, and shipment produces status. And then we want to say that the enactment generates all of the protocol's parameters. So remember, we had this parameter line, and now we are saying the enactment generates all these parameters, so we make them all of them out as well over here. So now you have the complete protocol specification. That's it. You interpret the requirements, you specify the meanings, and based on the coordination requirements, you introduce some causality in the protocol. Now, how flexible is this protocol? So we have a lot of tooling. We have verifiers, we have programming models that you can use to implement the protocol. I'll talk about that in a minute. But this protocol has 630 different parts through it. That other protocol could not handle 2 parts, the informal one that I showed in UML. It could not handle 3. But this one has 630 different parts. So for example, seller sends offer, seller sends shipment, buyer receives shipment, and so on. Or seller sends offer, buyer receives offer, then buyer can send an instruct without sending an accept to the bank. It sends an instruct first and maybe sends the accept later. Or maybe the seller sends an offer and sends a shipment straight away, like this one shows. You would not have imagined that based on the requirements, but it's possible, right? If the seller knows the buyer and has made an offer, but the buyer has not responded for some reason, then the seller could say, oh, well, I know this guy. Let me just go ahead and send the shipment. I know he'll pay up. So in business reasoning, we use all this kind of flexibility, but our current approaches cannot capture this in the protocol. And in this approach, you can capture. In the BSPL approach, you can capture. So it has 630. You can run our tooling. It has 630 parts through it, which is super, super flexible. And you can make it even more flexible. I didn't introduce a more flexible protocol because it'd be longer and take longer to explain. Okay, so we have a protocol. Now we have a blueprint for the system, right? We have a blueprint for the e-business system. We have the architecture. Now we want to implement its endpoints, the agents, based on the protocol. So think about, any reasoning based upon protocols involves state, right? So the current state of the protocol in the agent tells the agent what it can do next. That is just general reasoning about protocols. Now, here our agents have local state. The local state it's the history of messages it has sent and received, right? So it's just all its communication. And based upon its communications, it can determine what other messages can it send. So for example, if the seller send local state the log is just this message over here. So it sent an offer with ID 1. Then that means in that state, it can send an offer with some binding for ID value, ID item and price, because these were all out. So it can always send a new offer. There's no constraint on it. And in the interaction, in the enactment with ID 1, it's enabled to send a shipment. Okay, so there are only 2 messages that the seller sends, offer and shipment. And because it sent the offer, therefore the shipment is now enabled in enactment 1. So these are the 2 moves it can make in the state, right? So now what we have is a protocol adapter that encodes this reasoning. It captures the state. It sits over the network, captures the state, maintains the local state, and tells the programmer through this programming model interface what are the things it can do. So what are the enabled messages? And then the programmer fits in custom reasoning to say, so for example, so this is this is a reasoning for the seller. So you can write code like this in Python using a framework where every day at 5 o'clock, it looks at all the enabled messages and gets the enabled shipments from it and sends them all by setting status to Monday. So whenever a shipment message is enabled, in this case, it's sending them. But you could write more complex code where you say that, okay, my shipment is enabled, but have I received an accept from the other guy? Only if I've received an accept from the other guy, then I want to send the message across. So you could modify it. Or you could even go ahead and say, well, it's not enough to receive just an accept. What I want is the transfer from the bank. Only if I've seen the money, then I'm going to send the shipment across. So you can plug in all this logic over here. But the protocol supports all that. So you could fit in the business reasoning over here as you want. So the agent's business reasoning, the business logic, that's what the programmers want to focus upon. And that's what they get to focus upon because the adapter abstracts away the message ordering and all that stuff from the programmer. Okay, so this is my message for you guys. So interaction protocols are a fundamental architectural abstraction. If you want to actually build decentralized, loosely coupled systems, then you have to model the protocols. Today, we don't model the protocols. We write them in low-level code, but we should go beyond that. Actually model the protocol. It'll make us life much easier. If you want robust, loosely coupled, flexible systems of agents, Stop thinking in terms of message ordering. Stop relying on complex communication services. Specify meaning. Meaning is crucial. I think everybody will appreciate that. And causality is a notion I've introduced here. It's also a fundamental notion. I hope you reflect upon that. Specify meaning and causality. Specify, verify, and implement information protocols. Okay, so our stuff is here at this URL on GitLab, gitlab/mazar/bspl. So you can try it out. And please chat me up. Thanks.